Welcome to 16.3a. We're going to talk about electric fields today, and I just want to highlight that we're only doing one-step problems. We're not doing problems like in Sample D. So what we're going to do today is we're going to calculate electric field strength, and we're going to draw and interpret, which means understand electric field lines. We'll save talking about conductors for the next video. So when we talk about an electric field is just an area around an electric charge where an electric force can be found by using a test charge. Okay? So we draw electric fields like this, and we're going to understand what that is in a minute. But we know that field exists because if I put some other charge out here, whether it's plus or minus, it would either move towards it or away from it, okay, because it'll be either attracted or repelled. And so we know that there's a field there. Just like if we talk about, we have the Earth, right? If this is our Earth, we know if we take anything, like a person, and we drop them, they're going to be moved towards the Earth. So there's field lines around the Earth too. Okay. So with this electric field, okay, I really want to point out, right, that again, if we have some charge here, okay, this is our test charge. Okay, and our book calls this Q0, but we could call it anything that we want. Okay, if this charge is positive, right, we know it will move towards there. Okay, and if this charge is negative, we know it would move away. Okay, and depending on where we put it depends on the amount of force that would draw the charge to it or away from it. Okay. So with that, an electric field's direction is defined as the direction a positive charge will travel when placed in the field. Okay, so this means this positive charge here, this is our test charge. So if our test charge is always positive, okay, what direction will it travel? That's the direction of our electric field. Okay, so if we have a big negative charge here creating our electric field, and we put our test charge here, right, it's positive, so that means that it will go towards it. So that means that's also the direction of our E field. Okay. Now if instead we had a big huge positive charge, okay, and we put our little test charge by it, okay, it's also positive, well, it's going to move away from there. Okay, that means that our electric field is also directed away from the charge. Okay, so negative charges get electric fields drawn towards it, and positive charges get fields drawn away from it. Okay, so now if we're looking at calculating this, we first need to remember that our electric force is equal to this equation, okay, where we have our two charges here, and what they've done here is this is our charge creating the field. Okay. And like I said, they use Q0 as our test charge. Okay, so that would be the force if we were calculating the force between the two, right? And remember, it's over the distance squared. Okay, so now if we want to calculate electric, what we do is it turns out to be the force divided by our test charge, because we don't want to know the field strength that involves our test charge. So if we divide that force by the test charge, they cancel out, okay, and that's us with the electric field strength. Okay, so E, I used it just a second ago, but E is our electric field strength. Okay, and it's caused by a charge. Okay, and we're going to still use Coulomb's constant. We've got the charge creating the field. Producing means creating it. And it's still an inverse square law because it's still over the distance squared. Right, so the electric field, just like the force, okay, drops at 1 over r squared. Right, just like force does. So both force and electric field, okay, both of these use this 1 over r squared. So as we look at that now, let's see if we can figure out, do an example of calculating the electric charge. And this would be an example like a question you might see on a test, because we're not doing the sample problems like in the book. So it would be something like this. So we're going to start out by writing our equation, okay? And we know the electric field is going to be equal to our Coulomb's constant multiplied by the charge divided by r squared. Okay, so if we look through the information that we have now, we've got a charge, Okay, Q1 is 5 microcoulombs. It's 8.8 meters from a test charge, which I called Q2 this time. That has negative 3.0 microcoulombs. What is the strength and direction of the electric field experienced by the test charge? Okay, so we're going to use this to calculate the strength, and then we'll look at how we figure out the direction. Okay, so in this Q this time is going to end up being Q1, okay, because it wants the strength of the field experienced by the test charge. This is our test charge, so this is the one creating the field, okay. So we know that Q1 equals 5 microcoulombs, okay. Remember, micro means times 10 to the negative 6th. You need to remember that. So it'll be 5 times 10 to the negative 6. Okay, coulombs. Then it says it's 0.8 meters, so that's our distance. Okay. And then we've got the test charge, but because test charge isn't part of the equation, we don't actually care and we don't need to worry about that information. That does not matter. Okay, and I want to point that out, okay? The field strength does not depend on the test charge strength. That's really important to understand. Okay, so going back to our calculations now, we should remember from before, hopefully, that our Coulomb's constant is 8.99 times 10 to the 9th. Okay, and now we have all the information to calculate the strength of our charge. So going back and plugging everything in, we're going to have E equals 8.99 times 10 to the 9th times our charge, which is 5 microcoulombs, so 5 times 10 to the negative 6th coulombs, divided by our distance squared, so 0.8 meters squared. And when we plug all of that into our calculator, our answer comes out to be 210.7. Okay, now we need to think about what the units are going to be here. So to think about the units, I want us to come back and think about the original equation where it's force divided by our test charge, because that gives us the units most easily instead of going through the units here that I haven't written out. So the unit of force is the Newton, and the unit of charge is the Coulomb, so our electric field just simply ends up being newtons per coulomb. And that is our final answer for our electric field strength, okay? But what we need to look at last is the direction now of the charge, okay? So our test charge here this time is negative, okay? And electric field strength is defined as positive. So even though these two charges, Q1 and Q2, they'll be attracted to each other, our field is going to be directed away because it's based on a positive test charge. And a positive test charge, would be forced away from a positive charge. Okay, so our electric field direction, okay, is away from the charge. So now let's look at how we actually draw these electric field lines so that we can understand them a little bit better. Okay, so electric field lines are lines that help us understand the strength and direction of the electric field. Okay, they don't exist in reality, okay, but they help us visualize, which means imagine what is happening around a charge. Okay. So one way that we can visualize these electric field lines is if you take a charge here and you set it in some seeds, the seeds will all line up because you've got a polarizing effect. Okay, because this is a temporary charging. Okay, that causes them to be charged temporarily. And so they line up along where field lines might exist. Okay, so you could kind of see, maybe there's a line here. Let me make this pen just a little thicker so you can see it more clearly. Right, so we might have a line here, and we can kind of see, a line going out there, and a line here. Okay, so that kind of tells you the direction of the electric field. But again, just because you see all these lining up doesn't mean that these lines exist. As you can see, they don't follow the straight lines necessarily. Okay, so this kind of is one way to help us visualize electric field lines in reality. Them. Okay, so there are several rules we use when drawing electric field lines. Okay, they're always drawn in the direction of the field. That makes sense. Okay, they extend out perpendicular from the surface of the charge. We'll look at what that means here in just a sec. Okay, the number of lines represent the strength of the field, so more lines equals a stronger field. And field lines cannot cross each other. Okay, your book phrases these a little bit differently, but I feel like this makes those rules much more clear than it is stated in the book. But ultimately, it's saying the same thing. So what we've done here is our first one. We're going to look at these first two ones first. So lines are drawn in the direction of the field, okay, and lines extend out perpendicular to the surface of the charge. Okay, so here's two examples of what that looks like, right? So we've got a positive charge here, which if our test charge was positive would force it away, so the arrows point out. Okay, now if there's no other charge, you see this line, it's saying it's not actually near that other charge. Okay, but these lines theoretically just go on forever. Okay, they do not move or change until they interact with another charge. Okay, and a positive test charge then is also attracted to a negative charge, so you can see these arrows are directed towards the negative charge. So these are our two most basic kinds of electric field lines. Okay. Here also the third rule is that the number of lines represent the strength of the field, more lines being a stronger field. So if we look at these three examples, right? All of these you should be able to identify because the charges going out, these are all positive charges, okay? And this one only has just a few, right? This one has 8, this one probably has 16, and this probably has 32 if we counted them all out. So we can see that this one has the strongest, okay, the strongest electric field because it has more lines. And this is the weakest electric field because it has the least. Okay, so this one's just in the center. So the number of lines tells us how strong the field is. Okay, also field lines cannot cross each other. Okay, so in other words, if we have two charges, okay, and you might be wondering, well, if I have a negative charge and a negative charge, right, the field lines from this one extend, oops, excuse me, I drew that line wrong, let me erase that, okay, they extend towards the field from all directions, right, okay, and they're coming in perpendicular, so they come in to land straight. So what's happening with this charge, right, we might want to imagine that they do this, okay. But then we get these lines here that cross in these spots, okay? And we can't have that happen. So how does it end up looking like in reality? Okay, well what happens actually is the charges diverge. Okay, so if you have two like charges, instead of their lines crossing, they split out like this. So they never touch, they never cross. Okay, and if you had a positive and negative charge, okay, they'll go from one to the other. So again, we don't get straight lines that cross. It turns out that they go in this curved path, okay, that kind of connects the two charges. Okay, so how do we know that that's actually the pattern made by field lines and that they don't actually cross? Okay, well, we can go back to our grains of seeds to see what happened. Okay, so if we take two seeds, okay, or seeds, and we take two charges and they're the same, we get this pattern where these field lines kind of bend away from what's going on and then they're normal in the back. Okay, and the same thing happens then if we have two opposite charges, then we can see that these lines curve towards each other and they create these curves. So you can see how this diagram mirrors what we can see in reality, and that's how we know that these electric field lines don't really cross. Okay, so I just want to look at some examples here, okay? So if we have two charges, okay, we know that one of these is positive and one of these is negative, okay? So we can tell if we look over here, the arrows are pointing towards Q1, so Q1 is negative, okay? Q2, the charges are going away from it, so Q2 is positive, okay? So now that we've identified that based on the arrow direction, we can also notice that Q1 is going to be greater or stronger than Q2 because it has more field lines. Q2 only has 4 field lines. Okay, and Q1, if we count them, it's got the 4 coming into it, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. Okay, Q1 has 16 field lines. So Q1 Okay, Q1 is 4 times as strong as Q2 because it has 16 field lines to the 4 from Q2. Okay, and notice these extra field lines that Q2 doesn't have don't connect to anything. Okay, so the number of field lines indicates the strength. Now this is just for fun. I just wanted to show you what this looks like. We can't tell direction, okay, but we can get some really funky patterns when you have more than just 2 charges, okay. So what we can tell, right, is that these lines are connecting to this one, right, but they're going away from this one. So these two have the same charge, okay. And then if we look here, these ones are also diverging, okay, so these are also the same charge. Okay, and these 2 charges that are the same are opposite. Okay, because we can see the lines connecting them, right? These ones go here, these ones go here. Okay, same thing. These ones go here, these ones go here. Okay, so we can see that they are connected. So we can always tell, even if we don't know if they're specifically negative or positive because there's no arrows, we can actually tell which ones have the same charge and which ones have opposite charge based on where the field lines go. So this last picture then is just kind of a fun one. It was created by MIT, and I like it just because it shows the light. Okay, here also we can tell what kind of charges, or the relationship of charges. So we can tell that these 2 out here, okay, are opposite because their field lines go towards each other. Okay, and same with these 2 in here, right? The field lines are connecting them. But here, these 2 are the same because their field lines meet and diverge. So just kind of another fun example of a way we might imagine how field lines look on charges. So that brings us to the end of 16.3a. We'll get a chance to practice all this information in class, so go ahead and let me know if you have any questions there.